Today we're going to be going over 8.4 Fluids and Conservation Laws in Unit 8 of AP Physics 1. So, what is this unit really about? So essentially, there are two big conservation ideas that govern the movement of liquids. So number one is going back to the conservation of mass, which is related to the continuity equation. And basically this states that mass flow rate stays constant through a pipe. And then the second idea is the conservation of energy. Which basically states that through Bernoulli's equation, pressure plus kinetic energy plus gravitational energy remains constant. All of this remains constant along a streamline. So together, this all explains why water speeds up in narrow spaces and in narrow pipes. It also explains why airplanes fly, why pressure drops when velocity is increased, and also why fountains rise lower than building height. Now, let's talk about more deeply the continuity equation. So let's make some space for this over here. Essentially, A1V1 is equal to A2V2. So A means cross-sectional area, and V means the fluid speed. And the subscript 1 and 2 is just the location in the pipe. So it's basically just a location indicator. And this is derived from PA1V1 is equal to PA2V2 with density canceling for. So then P cancels out because density cancels for incompressible liquids. Now, here are some statements that you need to memorize. So first is that if area decreases, velocity will increase. If area increases, velocity will decrease. Also, if you have a wide river, then it will be a slow flow. But if you have a narrow river, it'll be a fast flow. Okay. Also, hose. What is it? A hose nozzle speeds up water because the area shrinks. So that's why when you have a hose, it can squirt water really far distances and pick up the speed. And that's why it can also make the force of the water a lot stronger. So the formula for the cross section of a circular pipe is gonna just be A is equal to pi r squared, just the area of a circle. Now let's move on to mass flow and volume rate and volume flow rate. So the formula for volume flow rate is just going to be Q is equal to AV, and the units are going to be meters cubed per second, and the mass flow rate is just going to be equal to M is equal to pressure times AV, with the units being in kilograms per second. And what you need to know is that when a pipe narrows, then the volume flow stays constant. Also, you need to know that velocity changes to keep Q constant. Next, let's talk more deeply about Bernoulli's equation. So let's make some room for that over here. Yeah, let's make some room for that over here. Where was this? Okay. Not quite sure, but we don't need that. So the equation for Bernoulli's equation is just P plus 1/2 PV squared plus density times gravity times height is going to be constant. And so all the variables, P is just pressure energy. And 1/2 PV squared is just the kinetic energy density of the moving fluid. And PGH is just going to be the gravitational potential energy density. So some things that you have to memorize about this is that, okay, let's move this down a little bit here. So some things that you have to memorize about this is that fast fluids have lower pressure. Also, higher elevation means lower pressure. Also, higher fluid speed also means lower pressure. For example, air over a wing. So let's talk about the special cases for Bernoulli's equation that you have to know about. So some of the special cases that you need to know about include horizontal flow, which means they're at the same height. And what this basically means is that H1 is equal to H2, And that means that in the equation, it's basically you're just going to set up your problem to look like this. Pi plus 1/2 PV1 squared is going to be equal to P2 plus 1/2 PV2 squared. So essentially it's the same equation, but just with the different subscripts. And you're basically going to use this setup for these following scenarios, which includes comparing pressure in pipes, the Venturi effect, and also for airplane wing lift. So from this, you're going to use this and you're basically going to factor out the 1/2, and then you're going to solve for pressure difference. And it's going to look like this. So it's going to be P1 minus P2, and then you're going to put that on the one side. And then you have this factored out, just leaving you with V2 squared minus V1 squared. So, and then this is for the first case. Now, for the second case, we're going to have equal speeds, aka same velocity. So what this means is that V1 is going to be equal to V2, and that means P1 plus PGH1 is going to be equal to P2 plus PGH2. And this is used to solve open containers, water towers, and also fountain height predictions. So let's move on to our next section, which is going to be interpreting real life examples and using this unit to do so. So let's start with the airplane wing. So on the airplane wing, you're going to have to identify that air on top, it moves faster. Therefore, the pressure is lower. And also that means that the air on the bottom moves slower. Therefore, the pressure is higher. And also the net upward force is the lift that's making the airplane fly. Now let's move on to the hydrant or the nose or the hose nozzle. So for this, you basically have to just remember that smaller area means higher velocity. This is from continuity. Oh my goodness. From continuity. And also that higher velocity means lower, okay, that means pressure is lower from Bernoulli. Now let's talk about roof blown off in storm. So basically, high speed above the roof is basically gonna mean low pressure. And the height, it stays the same. So that means the pressure decreases. And here is, after this, let's talk about when to not use Bernoulli. So be on the lookout for these, because it will try to trick you. So basically, avoid it when the fluid is viscous, turbulent, not incompressible, has significant friction, / losses, or if you're examining across two different fluids. Different fluids. Also, if the streamline crosses. So let's continue with this. Also, you can't have when the streamline cross / not steady flow. Also, you need to know what assumptions are necessary. So assumptions that are necessary for using the equation include that it is, again, an incompressible fluid. Also, that it's non-viscous. There is a steady flow. And also that it is in the same streamline. So, let's write about when you use the following. So, you use continuity. You use continuity when the use of this is when you have pipes, hoses, and rivers. And for the volume flow rate, QAV, you will use this when you have faucets and also for pumps. For the mass flow rate, you will use this when you have fluid transport. For Bernoulli's equation, you use this when you have pressure volume comparisons. And you use pressure difference, which is the alternate version of Bernoulli's equation down over here. You use this when you have the Venturi effect again. And then you use P plus PGH when, let's see, where did we put this? Oh, right here. This is for the Venturi effect. And then P, this P plus PGH equals constant if V is the same, which basically means that pressure decreases with height. And you use this for water fountains and for water towers and fountains. Bernoulli's equation essentially is the conservation of energy. Yeah, we wrote that up there. Mass per second plus, okay. Now, here are some principles that you just need to like ingrain in your head. Otherwise, you're gonna run into some problems. So some principles include continuity, which is that area increasing means that speed will decrease. Area decrease means speed increase. From Bernoulli, we have speed increase means pressure decrease, and height increase means pressure decrease. Also, pressure is energy. Pressure is, oh my goodness. Pressure is energy per volume. Okay. Also, now you need to remember that fluids move from okay, this is for fluid movement. So remember that fluids move from high pressure to low pressure. Also, they move from low velocity to high velocity. One area changes though. Also, note that fluid density matters for pressure terms.